Well, I'd like to welcome Jason Skufca from 9 Energy Services. I've known Jason a long time from his time with BJ Services and then Baker Hughes. He subsequently left Baker and went to join ConocoPhillips and is currently with 9 Energy Service, where he's the engineering manager. He's based in Houston. Jason has been a long time ICoTA supporter. He served on the board of directors for the US chapter, and as well as being the senior chair of the ICoTA International. He continues to assist with the program committee for the annual SPE ICoTA International Conference. So, Jason, thank you for joining us today, and I'll let you jump straight into your presentation.
Thank you very much for that, John. It's always a pleasure hearing your voice. So the title of my paper is A Force to be Reckoned With, the Effects of Extended Reach Tools on Plug and Mill Operations. This was a paper that was put forth for the recent 2020 ICoTA conference in the Woodlands, which was unfortunately canceled due to the pandemic that we are all still under today. So going through here, let's see if I can actually get my presentation to work. All right. So as we're working on the wells, we're seeing an increase in lateral lengths. Oftentimes now these laterals are extended beyond 10,000 feet. And of course, that creates some challenges for coiled tubing. Back when I started, 1 3/4 was kind of our big pipe. Then we went to 2 inch, 2 3/8, and now we're trying to tackle these with 2 5/8 inch coiled tubing strings. So to be able to accomplish these extended reach wells, we usually take on a multi-tiered approach. And that may include all of the above here, or all of what I'm talking about is addition of chemical pipe-on-pipe lubricants. This is probably the cheapest method to try to help us reach target depth. They are actually fairly effective. However, in a plug mallet operation, we'll see a lot of wellbore debris, sand, and of course the plug parts themselves. And these are, by the name implies, pipe-on-pipe, not pipe-on-debris lubricants. So you definitely get a decrease in effectiveness whenever you're dealing with a wellbore full of sand. We can optimize the string design. There's a paper that I co-authored that was also presented earlier this year, which was the 199843. And so this is really kind of looking at individual wells and optimizing the taper designs to apply more weight on bit. What I would usually see is about an increase of anywhere from 800 to 1,000 feet or so with having to optimize string design. And then of course the last one is really the topic of this paper, and that's the addition of these extended reach tools. And if we break out the extended reach tools into 2 sub buckets, we have in there mechanical inertia tools and flow interrupting tools. And for coiled tubing, the most predominant method is these flow interrupting tools. And as you may know, there's several of these out on the marketplace today. They all use a different mechanism to give that flow interruption. So there's a rotary valve, a poppet valve, and a fluidic flow modulation, just to name probably the top 3 in the marketplace today. And what I'm seeing in the industry today is that these tools are relatively inexpensive. So for the cost of the whole entire service that's out on location, adding a ERT on the end of the coiled tubing for the additional $1,200 or whatever it costs is pretty non-significant. So regardless of if we need these things, our customers are still running them. So I easily say 99% of all the coiled tubing intervention drill outs were running an extended reach tool. And so that brings us to the challenge of how do we go about modeling these tools on the end of our coiled tubing? So the most common model in the marketplace today that's easily accessible by the majority of independent coil providers, has some default model assumptions. And these assumptions basically integrate a friction reduction factor. So many pounds force of friction reduced per barrel per minute of pump rate. And that ratio was really developed back, I think now we're pushing probably a good 15 years from some testing that was done. And since then, these tools have become much more powerful. So I think that some of those defaults, those assumptions are kind of no longer valid. The newer tools on the marketplace have some modeling available, but they are kind of proprietary. So as these tools are proprietary to the tool service companies, so too are the models. And so they may not be really accessible by the end user. And regardless of which model we're using, I think there's definitely a combination of not only a friction reduction factor, but also a tensile end load that's applied onto the coiled tubing. So then we have the modeling, and then of course, what is really happening downhole? And so that led us to the development of putting together a memory tool. And so this downhole memory tool will measure our tension and compression. So this is our weight on bit. Measures the torque, the downhole pressure, downhole temperature, and we'll also look at lateral and tangential vibrational forces. And with this tool, we have recorded over 1,500 plugs drilled. So I'm going to go into some case histories now. And I know I'm presenting for the Canadian chapter, so I apologize in advance that these are all API numbers, or US numbers. So you have to kind of do your own conversions in your head. But our first case history here is that's 5.5 20-pound casing. Kick off at 9,820 feet. We ran 2 3/8 coil tubing with a 2 7/8" PHA. This is an interesting case history in the fact that we had 2 runs. The first run and pull was without an extended reach tool, followed by a second run with the extended reach tool. And so I'm going to show you the data here, and as I go through these plots, I may tend to round some numbers, so forgive me for that. So this first case history plugs, this is at 10,736 feet. Again, no extended reach tool. So we go in, and I'm looking at an average run and pull weight. And so if you look in detail of a graphical representation of coiled tubing weight, there's not exactly a number. So just based on the injector head sitting on a pivot point, the coiled tubing running in sinusoidal buckling or worse yet, helical buckling, all that's going to play into how that weight indicator reads at surface. And so what I'll do is I'll take a period of time and just kind of take an average. And so in this particular case, our average run and hold is 7,470 pounds. We then tag the plug. I'm sorry, let me describe also. Our depth here is in this maroon color, and the y-axis on the right is our depth, y-axis on the left is our weight. Again, that is in pounds force. And then our time is on the x-axis. So we run and hold to this plug, and we tag it, and you see right away that our surface weight drops down all the way down to 3,287 pounds. And so we refer to that as a slack off weight. So the slack off weight is simply our run and hold weight minus our minimum surface weight. So this is what we're putting into the system. So we put in 4,180 pounds. So now I'm going to bring in our downhole data. And so this is our downhole weight on bit. So this is just above the motor recording. And so when we tag that plug with that 4,180 pounds of slack off weight, we're seeing an initial weight on bit of 3,224 pounds. In this particular example, or with this particular tool company, they would kind of, as we returned our surface weight back up to neutral, they would then go ahead and slack off some more weight. So you see the sawtooth pattern occurring until we're through the entire plug here, which took about 20 minutes. But I just picked a different point here of this additional slack off weight. And so we're slacking off 6,400 pounds, and that's yielding a maximum weight on bit there of 4,754 pounds. So now it goes to try to model this. And so I'm looking at different friction coefficients because we don't have the extended reach tool. And so I'm plotting anywhere from a 0.3, which by the way is the default of one of the most popular models in the marketplace, all the way up to a 0.5 friction coefficient. And so at this depth, the 10,736, I put in a slack off weight of 4183 from our example, and then our given weight on bit from the downhole memory tool of 3,224 pounds. So you can see we are far below anything that the model would have predicted, way below even a 0.5. So we are outputting a lot less weight on bit than what the model predicts. Now, if I go in, and I don't show this in this case, but if we go in and do a friction match, we can actually friction match overall the weight, taking out the slack off weights during the plug mill outs, and we'll see about a 0.24, 0.25 friction coefficient. Another example without the extended reach tool here is a little bit deeper into the well. So now we're 11,255. Again, taking our average weight of 6,490 pounds, all the way down to a slack off weight, minimum surface weight of 1127, giving a slack off of 5363. Bringing in our downhole weight on bit in black, and we're seeing our initial weight on bit of 3,500 pounds roughly. And then again, you see as our surface weight returns to neutral, that we continue slacking off until we are through this plug in around that 20-minute mark. So took this area here, so slack off weight of 5,300 pounds, yielding us weight on bit of 3,700 pounds. So back to my sensitivity modeling again, slack off weight of 5,363, weight on bit of about 3,500 pounds. Yes, we are kind of close to that 0.5 friction coefficient, but I think anybody would agree that that is a very high friction factor to consider in a cased hole wellbore. If it was indeed 0.5, we would have a very difficult time in reaching TD of the well, which we did not. So you saw the couple times there in roughly about 22, 25 minutes per plug. And so our customer got anxious and got tired of waiting for a normal plug and mill out time of the 20 minutes. And so we tripped out a hole and put on the extended reach tool. And this is a fluid flow modulation type of a tool. And so we go back in, and this is at a plug depth of 13,000 feet. And right away, of course, we notice that our surface weight is much higher. We're now in the 15,000 range versus before, even at the shallower depths, we were about 6,400 pounds. So right away, we gained a lot of weight back. So we tag the plug and we go down the minimum surface weight of 10,300 pounds, yielding a slack off of 5,100 pounds. Bringing our weight on bit and picking our initial weight on bit, I'm seeing a 6,000 pounds. But a little bit different here. What you see is actually the weight on bit is increasing. So it increases all the way up to 7,500 pounds in this particular example. We'll go back real quick. Also note that you do see the sawtooth pattern, as we saw before, as our surface weight returned back to neutral, they slacked off more. But in this case with the extended reach tool, we do not see that same sawtooth pattern as we had seen on the prior examples. So now trying to do the sensitivity analysis, I took about the same approach. I looked at different friction coefficients, but in addition to the friction coefficients, I also added the tensile end loads to try to approximate where we are with this tool on the end of the coil tubing. And so in this case, we had a slack off weight, 5,100 pounds, and our initial weight on bit of 6,000 pounds. So where that crosses is fairly close to this 0.2 friction coefficient and a 3,000 pound tensile end load. If you talk to the tool manufacturers, you would find out that, yeah, they'll agree that these tools probably yield a 2,000 to 3,000 pound end load. And the 0.2 is probably not super, it's not really out of the question, I would say, with the high flow rates that we had with 2 3/8 coil by the 5-inch casing. So that kind of matches there. However, as you saw in that graph, our weight on bit continued to increase all the way up to 7,500 pounds. And so now we are outside of the round, as you see in this dot, of what I would consider anything that's really probable for what these tools can do. So I put the graph side by side here from our examples on this first well. On the left is our no extended reach tool, and on the right is with that extended reach tool. And as you can plainly see, these are very different signatures. On the left, as our weight on bit, or as our surface weight comes back to neutral weight, our weight on bit decreases. This is what common thinking would tell us would happen. On the right, as our surface weight returned to neutral weight, our weight on bit continued to increase. So a little counterintuitive with the extended reach tools. So now I'm going to move on to another case with some bigger coil, and which will also lead into a subsequent kind of extreme example case. So in this well is 5.5 23-pound casing, kickoffs at 7,700 feet, 2 5/8 coil, and a larger BHA. We're running a 3 1/8-inch extended reach tool with the Poppet valve style extended reach tool. And so now we're going to look at a plug here at 14,722 feet. And so our average run and hole weight before tagging this plug is about 16,500 pounds. Our minimum surface weight drops down to 10,350, yielding a slack off to 6,120 pounds. So I bring in our downhole weight on bit gauge. And so our initial weight on bit starts off at 6,000 pounds, and it grows all the way up to 11,700 pounds. And so trying to model this with our sensitivity analysis, again, looking at different friction coefficients here and different tensile end loads. And our initial slack off weight is 6,120 with our initial weight on bit of 6,100 pounds. Kind of gives us in the crosshairs of between the 0.2 and 3,000 tensile, or 0.15 and 2,000 pound tensile. So either one of those, probably the red dotted line is maybe more in line with a 3 1/8 Poppet style extended reach tool. But as we saw again, that our weight on bit continued to increase to 11,700 pounds. And so that puts my dot up here in my title area for this slide. So far outside of the range of what I would say a model would be able to predict. So on this same run, we had a little bit of interesting phenomena. So as we continued to run in hole, we started to detect that really we're not seeing the pressure differential from the motor. So our tool supervisor from the tool company wanted to try to give some weight on bit to see if he can build up any differential pressure to determine if the motor was actually working. And so that's what we did here, and we tried it twice, actually tried it 3 times. So this is at 15,780 feet. So we're running in hole with a average run and hole weight of about 16,000 pounds. And we kind of stair-stepped it all the way down, and he had us go all the way down to minus 8,200 pounds on our weight gauge. So we're a fairly extreme slack off weight of 24,000 pounds. And now I bring in our downhole memory gauge. And so as you can see here, our initial weight on bit was about 35,000 pounds, and it continued to increase to a maximum of 37,000 pounds weight on bit. So we picked up and decided to try it one more time. And looking at our second attempt here, excuse me. Our minimum surface weight now is minus almost 10,000 pounds. So a slack off weight of 25,000 pounds. And then looking at our maximum weight on bit, in this case, goes up to 41,000 pounds. They do try it a third time, but not to the same extent. So to me, it wasn't quite as exciting. But you see here that we put a lot of force into the system, and we're getting a multitude of that force out of the system. So now I'm going to move in and talk a little bit about the vibrational forces that we see from these tools. So the memory tool has G-force sensors in the X and the Y axis. And so what that means downhole is the X runs longitudinally with the coil tubing. Positive means towards the bit, negative means towards surface. And then the Y is our side to side. When we first built the tools, we had to pick a G-force sensor. And so an available one and one that we anticipated was sufficient enough was 25 Gs. After all, we kind of looked around at other G-forces, and so I kind of like this picture from flight training school. So this is what 7.5 Gs will do to your face. And so for sure, we thought 25 was more than sufficient. Unfortunately, we were incorrect in that assumption. And so then later we did upgrade the tools to 100 Gs. And so kind of showing this data, a lot more squiggly lines taking place. This is from our case history 1. This is, unfortunately, though, with that first generation tool with the 25G sensor. And so what we're saying here is, in black is my weight on bit. And then below this is the G-force sensors. And the blue is in the X direction. Again, positive towards the bit, negative uphole. And then the Y is the side to side in that light gray kind of behind it. So kind of as I would expect is as we are milling, so as we have weight on bit, you see higher vibrational forces occurring downhole. And then as we're traversing from plug to plug, those kind of diminish, and we're seeing still a good 5 to 6 Gs of lateral motion just from the motor, and then it's moving side to side around 10 to 12. But we're actually on the plug, we're exceeding that 25 G forces on the side to side load and pushing about 22, 23 on the lateral. So again, as you recall, we pulled out a hole and we put on the extended reach tool. And so this is our fluidic flow modulation tool. And so now the whole entire job, basically, we're saying the tool is maxed out 25 Gs, with a couple exceptions. When we have fairly high weight on bit, the tool tends to not necessarily stall out completely, but it definitely becomes less vibrant, if you want to say. So you will see around 20 Gs or so when we have these higher end loads on the coil tubing or on the bit. But for sure, plug to plug, we're maxed out at 25 Gs. So I do have an example here with our 3 1/8 Poppet style extended reach tool. Not exactly from the case history I showed you, but it's still the same diameter, 3 1/8, running on 2 5/8 coil. And so now this is our 100 G sensor. And so during the course of the job, plug to plug times, we're seeing in the X-axis, we are averaging probably about 50, 55 Gs, peaking around 75, 78. And then when we're actually milling a plug, we're seeing a little bit more side-to-side vibrations. We're actually peaking over the 100 G. So the 100 G sensor still is not enough to capture all of the data here. So these tools are really hammering downhole. There are a lot of forces happening, a lot of vibrations. Okay, so kind of giving a summary on the weight on bit that we're seeing. These are from my examples. So our 2 3/8 coil tubing from our case history 1 inside that 5.5 20 without the extended reach tool. we see putting a 4,100 pounds of slack off weight, so into the system, downhole, we're getting 3,200 pounds. And what I'm doing here is just taking the difference of weight on bit minus surface slack off. And so in all cases, without the extended reach tool, we get significantly less weight on bit than what we're putting into the system. Again, this is what intuition would normally tell us. Then we run our extended reach tool, and we put in slack off weight of 5,100 pounds and maximum weight on bit of 7,500 pounds. So we're getting significantly more in that case. We run the larger 3 1/8 inch extended reach tool, the Poppet style, where we put in 6,000 pounds of surface slack off weight, and downhole we were getting 11,700. And then my extreme example where we put in 24,000 pounds in, got 37,000 pounds weight on bit. So we're seeing fairly significant differences between weight on bit and the surface slack off. So kind of wrapping up here. So again, I've got data on over 1,500 composite frac plugs. All of the ones with extended reach tools, I would say, have very similar type of signatures of our weight on bit versus our surface slack off weight. Without the extended reach tool, weight on bit is less than the slack off weight, and weight on bit decreases as surface weight returns back to neutral weight. Again, this is what years of coiled tubing experience tells us what should happen. And what is a little bit news is that we're seeing our weight on bit is less than what the models predict. And so old rules of thumb of saying, hey, you have to have at least 500 pounds on your modeling. Maybe it actually should be more, because I think we're getting less than that without the extended reach tool. And from these plugs that we milled out, we're seeing an average of 20 minutes. These times coincide with all of surface testing that I've done with different plugs, where an average mill out time would be expected to be 20 to 30 minutes without a tremendous amount of weight on bit on the bit. So then we add our extended reach tool, and I'm saying that our weight on bit exceeds the slack off weight. And counterintuitive would be our weight on bit continues to increase as the surface weight returns back to neutral weight. Our weight on bit is much greater than predicted. And as would be expected with the high weight on bits, we do see a much faster average mill out time per plug. And then in these extreme examples, if we put a whole lot of force into it, excessive surface slack off, we'll get an order of magnitude of weight on bit downhole. And so what I have kind of deduced that with the extended reach tool, if we can reach there, if the tool will get us to that target depth, once there, then that extended reach tool will continue to apply sufficient weight on bit to drill through the plugs. And then the other thing is we're seeing tremendous forces downhole from these vibration forces. I do believe that these excess vibration forces are contributing to some coiled tubing issues, early premature failures, particularly at shallow depths of 2,000 to 3,000 feet while pulling out a hole. I know that there is some ongoing research surrounding those kind of unexplained failures, but I definitely think there is a tie-in between that and these extended reach tools. In addition to that, we also are seeing an increase in tool thread failures that are probably contributed to the vibration forces that are encountered downhole. And so that, Scott and John, that kind of concludes my presentation, and I'd be happy to open that up for any questions that anybody may have.
So we have one question that's been submitted so far. Just general point, if you have any questions, please either use the question tab to submit them or raise your hand, and we'll get to you. So we'll answer the question from Robert Gadenov, and it is what modeling software was used for simulation, if you're able to comment on that.
Well, I guess I can comment since I don't think this is an official SPE event. So I have access to two models. One is the NOV with CTS Cerberus, which is the one I was hinting at as probably the most widely used in the industry outside of the majors. And then the other one is a model from Baker Hughes called Skufca.
John, did you have any questions?
Can you hear me?
Yes, sir.
One of the things that I think your downhole tool has clearly shown, and that is when you slack off weight to start milling the plug, the coil tubing is stationary downhole. It may be moving slightly on surface as you slack off. So that raises the question of, were you modeling with a static coefficient of friction versus a dynamic coefficient of friction? Because there's at least a 30% difference. And maybe, but if you are static and there's debris in the well, maybe the difference is more than 30%.
Yeah, I have a hard time though believing necessarily that we're completely static, meaning up to that 30% or more range, given the amount of vibration that you see with these tools. That as we're milling the plug, you're seeing over 100 Gs of vibration, and yeah, I understand that that's going to have some attenuation length. However, on these jobs, there's probably multiple times to where you look over in this picture, you look over your left and you're watching that coil bouncing all over the place. So I don't know that we're ever in a static, a 30% increase.
Sorry, I should have been a little bit clearer. I was thinking of the cases where you weren't running the ERT.
Oh, okay.
And therefore you are seeing some
higher.
And when you attempted to model, you were seeing excessively high coefficients of friction to get agreement. So that would seem to support the fact that there is a static friction component.
Yes, I with you there. I mean, we did see, of course, the courses only went to 25 Gs, but we did see that it did increase as you're milling there, but that probably does have a fairly short attenuation length on the coil tubing in the lateral.
But with the ERT, definitely I would say there is no static friction. That's one of the reasons why using ERTs work better. It makes it easier to mill, because the difference between slack off and running doesn't involve a coefficient of friction change.
Right.
So we have a question. Sorry, we have a question from Ed Smalley. Very interesting presentation, Jason. Thank you. During the data collection for this project, do you have a chance to vary the flow rate through the ERTs? And can you make any comments on that?
On these particular case histories, like on a mill out, answer to that is no. However, I will say that I was involved with another data collection project looking at extended reach tools that was just looking at vibrational forces. And yes, then that one we did vary the flow rates and vary the densities and all that. So definitely saw an increase in vibrational forces with flow rate as one would expect. Also increase in vibrational end loads and pressure pulses with higher densities. But no, during these mill out processes, once it'd be kind of hard to convince the customer to drop rate or mess around too much. Let's go and do the job and pull out.
So I have a question. I did some work with a memory tool for well, accelerometer downhole in my previous company. And do you think that with 100 Gs of axial vibration, do you think that assists with getting unstuck or moving kind of debris out of the way as you're pulling out a hole?
Yeah, for sure. I was on a project actually where we had an extended reach tool, and also I think what you see is depending on how much tension, say if you are stuck, there's a sweet spot to where that tool will maybe hit harder, if you will, depending on how much tension you have in the coil along with the flow rate. And so I definitely have seen that, Scott, to where we were temporarily hung up, and kind of finding that sweet spot for our surface weight to where you started actually seeing vibrations at surface, from the coil movement. And once that occurred, it was, probably a matter of about 10 minutes that we kind of gained our weight back and was able to pull free. So it is definitely, I think, a side benefit that if you can get it working full effectiveness, that it can help out in those situations as well.
Yeah, that's interesting. We don't have any other questions that are submitted via the questions tab, and nobody's got their hands up. John, do you have any further questions for Jason?
I have one final question, and that is, did you look at the pressure pulses that were being generated by the ERT and try and then go back from that and calculate what the end load, the added end load you were getting as a result of the water hammer effect?
So I didn't really talk about the data acquisition rate. So we're taking data at 1 second intervals.
Oh, okay. That's a bit too slow, yeah.
Yeah, so my other data experiment, we ran our tool in conjunction with a high-speed pressure transducer, but of course that's not public information, but there you can actually see it. But yeah, I think these tools are hitting at what's, anywhere from 7 to 12 hertz or so, give or take. So we don't really see anything like that downhole.
Right. Okay, well, thank you, Jason.
Sure thing.